Okay. Alright, so today we're going to have our lecture on... Hey, get out of here. Okay, so we're going to have our lecture on the second lab. Okay, so that's going to be on the strain gauge. So we already did stuff on stress and strain with the extensometer. You know, that was week 2. And then we did that lab last week. Today we're going to have the lecture on the strain gauge, which is a different way to measure strain. So if we're looking at our homepage here, you should recognize this. I mean, this is a different extensometer here. But remember, the extensometer, that was used to measure deformation only. And we could use that deformation with our initial length for the rod that we have. And then we could measure, or we can calculate strain. For the second week, we're going to be looking at this kind of device here that you see that's kind of bonded on to this rod. And this is a strain gauge, which is going to directly give us a reading for strain. Alright, so if we click on this module for weeks 4 and 5, you know, I thought before that if I thought Canvas could be set up where we could click on this module and it would take us to directly this module here for weeks 4 and 5. I guess that's not the case, so you're going to see weeks 1 and 3 as well, but you know, just know that we're looking at the strain gauge and that's weeks 4 and 5, so week 4 is our lecture. So again, today we're going to be doing the lecture on the strain gauge, and at the end of the class, really it's probably going to take, we're going to be spending more time on the data reduction than the lecture today, but the last thing we're covering today is the data reduction for the first experiment. So we're doing this as a class. Now, the data that you use might be different than the data that I use. So to access the data for the data reduction for the first lab, click on Files on the left-hand side, and go to Experiment 1, and then click on Lab Data. And you can access the data for your group. So today what I'm doing for the demonstration, I'm going to use Group 2, just because Group 2, they had data for every single run. So for 1018 steel, 1045 steel, and aluminum. I think there was 2 groups in our class where you couldn't save or export the data for one of the runs for some reason. That wasn't an issue in any of my other sections, so we're still not really sure why that happened. So I don't care which data that you guys use for this data reduction. You can use the data that you have for your group, or you can use, you know, group 2 if you want, because that's what I'm going to be using for today. You know, I don't care, again, if you use group 2 or a different group's data. Really what I care about most is that you actually did the lab, you know, in person. Getting that hands-on experience is important, and for your memo, I just care that you actually understand, you know, what you see. For once we actually do the data reduction, that you understand, you know, what's going on, and you can explain it in your memo. Alright, so we'll talk about that, you know, once we get to that later in class today. And then also, I think I finally made the assignment for the memo, which is here. So that's due on September 30th. So remember, I extended the memo for the first lab by 1 week since we're doing the data reduction now as a class. But in the future, your memo is going to be due 2 weeks from the day of the lab. Alright, so let's do the lecture for today. So I finally got a Wi-Fi card on my PC, which allows me to share my screen differently, and it looks better. It looks better than sharing my screen through my laptop. Alright, here we go. Let's move this over one. Okay, so if you have any questions, obviously use your mic, or you can put it in the chat. So I'll try to look at the chat as often as I can, but it's on my laptop, so it's I'm not gonna see it all the time. This is kind of weird. I'm looking at my notes on the side, and I'm kind of blocked by my mic. Alright, so again, we're going to be talking about the strain gauge, right? So let's first define what a strain gauge actually is, or, I guess what its purpose is. Okay, so a strain gauge, it's going to measure strain by converting a change in electrical resistance to strain. Okay, so if you remember from our picture, let me go to that real quick. So our picture on our front page, that's a strain gauge right here, and this is bonded to a material, or a rod in our case. And what this does is it measures changes in electrical resistance, and that's converted to strain directly. So we're going to go over what that actual kind of formula looks like in a second here. You don't need to worry about the actual math too much. Really, the main takeaway for this lecture and for the strain gauge in general is just knowing or understanding that it's measuring changes in electrical resistance, and that's going to be converted to strain, and we're going to be able to read that strain directly. Okay, so what are the differences, from this and the extensometer? Because really, we use both of these. Turn that down a little bit. So we use both the extensometer and the strain gauge to really, in the end, get a value for strain. But how we get to that is different for each one. Okay, so they both measure, their own unique thing, and then from that we can get strain. So the extensometer, it measures deformation. We take that deformation, or that change in length, divide that by the original length, we get our strain. So that's stuff that we have to do ourselves. So we have to measure the deformation ourselves, and then, or really, it's logged straight to the computer like we saw in the lab. But we actually have to make that strain calculation ourselves. The strain gauge, it's measuring that electrical resistance, so that's something that we can read directly off. Or actually, it measures the electrical resistance, and then itself, it does the conversion for us to strain. So we don't have to do any calculations. It directly does that conversion for us right away, and all we have to do is write it down. So for us, there's really not much work at all that we have to do with the strain gauge. So we're gonna take both of these different methods for measuring strain, and we're going to compare them, and basically see in the end, once we do this lab, we're gonna see which one or which method is more accurate. So we'll compare accuracy. We're also gonna compare convenience, practical use. Which one is easier to set up? Which one is easier to use? To actually get our strain measurements. And so we're gonna compare all of these different things. Okay, so I don't want to spend too much time on the theory, but I'm gonna go back again. So I'm not gonna write a lot of this stuff down. I'll just kind of talk about it real quick here. So just to repeat myself, so this is a strain gauge, and so we have basically there's thin metal wires that you can't really see too well in this image, but they're in here, and that's applied to the rod, and it's gonna be, these are kind of situated parallel to the direction of strain, so that they're going to experience strain, these metal rods. And once they experience strain, there's a change in that electrical resistance in those thin metal wires. And that change in electrical resistance, that's converted to strain via a formula, which we're going to derive. And then we get our value for strain. Okay, so again, don't worry about the actual math too much. It's really just going to be here for a basis, so you can kind of understand how we're getting this change in resistance to strain. Okay, so we're going to start out from a point of a formula for resistance for our metal wires. Okay, so this resistance is going to be given by rho L divided by A. So rho, that's going to be the resistivity. So that's rho up top here. If that's not a P, it's rho. L, that's going to be the length of the wire. A is going to be the cross-sectional area. Okay, and then resistivity, if you guys don't remember, so I think you might have talked about it in like Q26 maybe, when you took that for physics. Or we might have talked about it last in, I don't know, like high school physics class or something. But resistivity, that's a material property, so it depends on the material that you have. It's a given though, so it's not something that we need to calculate or anything. But that's going to be, it's going to give us an insight to how much a material can resist electrical current. So if there's like low resistivity for a material, then it's not going to be able to resist current well. Current is going to be transferred throughout that material very easily. So again, this is a constant, and we don't need to do anything, any measurements for that. Okay. Okay, so what we're going to do now, we have our length and we have our area. We can take those two different variables, and we can convert that to volume, and then we're going to assume that the volume for our rod is constant, which isn't really true, but we're going to say that because it's going to make the math easier once we kind of go on here. Okay, so once we make that conversion from our length and our area, remember it's for a cylinder, so we have the length, the area, and we can convert that to volume. So this is going to be written as rho L squared over V, our volume. Okay, and once again, we're going to assume that that volume is constant, which isn't really true because, we're changing our length, we're changing our area, so it's not going to be constant. And what we're going to do now, and this is kind of a little hand wavy, I admit, especially when I first saw this, it was like, why are we doing this? But a lot of the times when you're doing derivations, right, some steps seem very hand wavy and random, but they're done to make things easier in the end. So we're assuming that the volume is constant, and now we're going to take the log of both sides here. Alright, and then what we're going to do from here is differentiate both sides, because really we want to look at a change in resistance, because that gives us our strain, if you remember. So if we differentiate both sides, or someone right outside my window. Okay, so differentiate both sides. And this is why we took the log of both sides, because now we can differentiate them and we can get a nice easy format that we want for the change in resistance. So this will be basically delta R over R, and then 2 dL over L. And then remember, our resistivity, that was a constant. That's a material property, and the volume, we assumed that that was constant. So this term here, all of that is a constant. Taking the derivative of a constant, that's just going to be 0. So all of that goes away. That's great for us. And again, that's why we assumed that the volume was constant. So let's rewrite this now to have deltas. So we're going to rewrite this as delta R over R is equal to 2 times the change in length over the original length. So now we have, a kind of setup here, a formula that makes sense to us kind of intuitively. We don't have any logs or anything like that. This is easy to understand. This is our change in resistance over the original resistance is equal to 2 times our change in length over the length. And well, the change in length over the length, that is a different way to write strain. So we can rewrite this again. So we are solving for strain, and then we're going to have our kind of setup for how our strain gauge is really going to measure strain. So I'm going to, there's really 2 steps here, but I'm going to do them both at the same time. So if we rewrite this and solve for strain, this is going to be epsilon is equal to 1 over 2 multiplied by our change in resistance over resistance. Alright, so that's our formula for how we can calculate strain or how we can obtain strain is a better way to say it. How we can obtain strain with our strain gauge. So our strain is going to be equal to 1 over 2 multiplied by the change in resistance over the original resistance, and that's what we have, again, for those thin metal wires. And all of this is done, automatically for us, right? The software is doing this calculation for us. It's looking at that, it's measuring that change in resistance, and it's computing our strain. And all we have to do is read it directly and write it down. Oh, sorry, there's a lot of questions. Well, a few. Yeah, I don't know who that was outside of my window. But, yeah, so you don't need to know the derivation. You don't need to remember it for lab. This is just to kind of give you background on what is actually going on kind of behind the scenes. Okay, so, let's see. Yeah, delta L divided by L, that's equal to epsilon. So remember that's how we calculate strain. That's our change in length, that's our deformation. Divided by L, that's our original length, and that is equal to strain. So that's something that we covered in the first lab, or first lecture. But that's strain. That's our change in length over the original length. Alright, so there's something that I go over sometimes, which is it's even more theory on the strain gauge, how we have different resistors in there, and we replace one of those resistors with our strain gauge, and that allows us to measure that change in resistance. But I don't think it's too useful for us as a lab, just because it's really getting into the theory. But if any of you want to know, if you want a little more info on how the strain gauge really works, you can stick around after class and I can explain that. But I don't think it's very useful for us. Again, I want to focus more on the practical side of the strain gauge, and obviously we're going to be using that in the lab. But there is one more thing to talk about, or a few more things, which is this number 2 here. So this number 2, in theory, it's going to be 2, but in reality, this, let's actually rewrite this. Okay, so, let me title this Calibration. Okay, so this 2 is kind of the theoretical value that we have. We just did the derivation for how we can calculate strain by measuring the change in resistance with our strain gauge, and then we can get a value for strain. This number 2 here that you see, this is, again, a theoretical value, but in reality, each strain gauge has a different kind of sensitivity to strain. So each strain gauge, it's calibrated from the factory to reflect that different sensitivity to strain. So you might see a value of 2, and again, all of this is done in the background. So your strain gauge might have a value of 2 here. Other strain gauges might have a value of like 2.1, 2.12, and it's usually right around there. For us, this is actually going to be 2.14. So let's write all of that out right now. Lower the numbers doesn't necessarily mean more accurate. It depends on your strain gauge. So each strain gauge has a different sensitivity to strain, so its change in resistance is going to be different too. So it's just unique to each strain gauge. Okay, so to kind of restate all of this, each strain gauge that you get, it's going to have its own unique sensitivity to strain. So what I mean by that is once that strain gauge undergoes strain, strain gauge A is going to have a different change in resistance to strain gauge B. So because both of these strain gauges have a different change in resistance, they each need to be kind of calibrated different to account for that sensitivity to strain. And that's done with the gauge factor. So in, I guess, ideal scenarios, I don't want to say ideal, but in theoretical scenarios, let's say that. In theory, the gauge factor should be 2, but because each gauge or each strain gauge has a different sensitivity to strain, it might not be 2. So for us, this gauge factor is 2.14. So that's all the strain gauges that we have in the lab. And again, you know what? It's like nice to know that it's 2.14, but all of this is already done again behind the scenes in the software. So you don't need to worry about this, which is nice. All we have to do is run our experiment, and we get the strain value directly from the software. Okay, so I'll talk about one more thing, which is how we deal with temperature effects. Alright, so once we're actually running the experiment, and this is the case for, basically all of our experiments, there's always going to be some effect from temperature. Temperature is going to affect our experiments to some degree. For some of them, it's going to be more so than others. I mean, for a really easy example, the Sharpie impact test, that's going to be a huge variable. So remember, that's when we have these different materials and we subject them to different temperatures, and then we see how they fracture under different temperatures. That's far out in the future from now, but I just want to say that, temperature, it's always going to have some amount of impact on each of our tests. So for the strain gauge, the specimen and the strain gauge, they're both going to deform a little bit for changes in temperature. So if it's hot, it's going to expand a little bit. If it gets cold, it's gonna contract a little bit. So to combat this, the strain gauge has what's called a dummy gauge, and that's placed on this kind of backing in a different orientation than the like actual strain gauge. and we can then use that to kind of cancel out the effective temperature. So let me draw this out and then we'll explain it a bit better. Okay, so in blue we have what is called the active gauge. So this is this strain gauge. It's orientated where it's going to experience the maximum amount of strain that the actual material is experiencing. So if we have this and let's say tension, okay, then this active gauge here is going to experience all of that strain that our rod is experiencing. So the strain gauge, if it's parallel to the direction of strain, then it's going to experience all of that. The dummy gauge here, we see that, it's kind of, it's flipped, or not flipped, but it's rotated. So this is rotated so it's perpendicular to the direction of strain. So it's not going to experience much strain at all. But both of these strain gauges or gauges, they're going to experience the same, or they're going to undergo the same change, or let me restate this. They are both affected by temperature the same. Okay, so since they're both affected by temperature the same, they're both going to expand or contract depending on the change in temperature. And also because the dummy gauge here, because that is not affected by strain, we can then account for that that temperature effect, and we can take that out. So it's not going to be again perfect, but we can manage that effect that temperature has on the strain gauge. And once again, this is done behind the scenes. You don't actually have to do anything yourself. The software is doing all of this for us. Alright, so if you're going to take anything away from this lecture, it's that the strain gauge is going to give us a strain reading directly, okay? Extensometer measures deformation, but we actually have to take that deformation, divide it by the original length, and then we get our strain. The strain gauge, it's doing everything behind the scenes for measuring that change in resistance. It's implementing our gauge factor, and it's also dealing with temperature effects. So it's doing all of that behind the scenes, and it's giving us the strain directly. Alright, so I know that this was like a really fast lecture and maybe a little abstract in a sense for how this is really measuring strain, because it's measuring that change in resistance again and converting that to strain. But that's the idea. But I just want you guys to, if you do have any takeaways from this lecture, is that the strain gauge, it's measuring that change in resistance, converting it to strain. That's all you really need to know for our lab. Okay, you want to understand the differences for how the extensometer can give us strain and how the strain gauge gives us strain. Okay, so before we do the data reduction for experiment 1, are there any questions on this? Okay. Alright, so if you have Matlab, which hopefully you have Matlab installed by now, you can open that up. Close out of that. Okay, so open up Matlab on your computer, and we're going to go over the data reduction. So, I'm guessing some of you haven't used Matlab in a while, which is fine. So we're going to need to go over some things in a little more depth. Also, if you just kind of want to watch this and, look back the video later, that's fine too. Do whatever you prefer. And for the other, experiments, the plan currently is I'm not going to do everything for you in the future data reduction videos, but for this one, I am. Besides one thing, I think, just one calculation. Just because I know some of you haven't used Matlab in a long time, so you're going to want to have a bit of a refresher. So I'm going to change this to the default color scheme. So there we go. There was something that I sent out in my email last night, which is that you need to install a toolbox called Mapping Toolbox. And so we need that to find our intersection point. So, later on in our script, we're going to find that intersection point, which is, our offset method, if you guys remember that, for finding the yield strength. So this add-on, to install that, make sure you're on the home tab here, and you're going to click on add-ons, and then type in mapping. Again, it should be the very first result. It's called Mapping Toolbox. I already have it installed, but if you don't, you're going to click on that, and then over here on the right, you should see like a download or install button, something like that. Download it. And, Matlab might need to restart, but it's very easy to install. Alright, so the first thing, let's make our location for the script. So I hope everyone is organized with their folders on their computer, but I know in reality that's not the case. But maybe take this as a moment to start to be organized, okay? So on the left-hand side, where's the add-on again? So go on the Home tab here in Matlab, click on Add-ons right here, and then search for Mapping. Okay, type in Mapping. It's going to be the very first result. Mapping Toolbox, click on that, and then on the, I don't know why I have that error message. Let's go back. Okay, Home tab, Add-ons, search for Mapping, and then it should be the very first one, Mapping Toolbox, and then over here, if you don't have it installed, it's gonna say like something like install or download. Okay, so again, hopefully you guys are organized, but if not, use this as a chance to be organized. So on the left hand side, you can see where Matlab is currently looking at. So currently Matlab, if I made a script now, it would be putting this script in, for me, in the path of home and then Patrick. Okay, so I'm gonna change this for our class. So it's gonna be depending on where you keep all of your documents, of course. Alright. So now you can see where your path is up top here. So for me, I'm in a folder for this class. Hopefully you have a folder for this class, alright? So you wanna put it there. And I'm going to make a new script here. So I'm gonna click on new script. And let's call this EGME 306A-10 and stress and strain data reduction. Okay. Now we can press save and we can actually save it. So this again is the folder that we're currently in. So I'll just call this experiment 1 class. For Matlab, you can't have any spaces in your file name. It doesn't like spaces, and you need to start it off with a letter. So make sure the very beginning of this file name has a letter. Okay, I'll save that. Next thing, we need to import our data. So again, looking at our current folder over here, you see that I have a folder called data. And again, I'm going to be using group 2. And we can see all of the data here. So we have 1018 steel, 1045 steel, and aluminum 6061T6. And we also have our Excel sheet that has the diameter data. Okay, so you don't need to put it in a folder. You could have everything in the same folder where your scripts are stored. But for me, I like having this separate folder for whatever data that I have. All right, so we're going to import that data. Also, one of the first things that we want to do is type in clear and CLC. So if you guys remember from Matlab, the clear command, that's going to clear all of our memory. So it's going to clear everything that we have stored in the workspace. We do that so we, if we're working on one script at one point and we go to a different script, all of that's still going to be in the workspace, and we want to clear out all of those variables that we currently don't need. Okay, and then CLC, that clears out all of our text. So if I have stuff in the command window, it's going to clear that out. Then I want to do that. You can go down here. Okay. So let's import our data. I'm actually going to pull up the script that I made last night, just so I have it kind of on hand. So you don't need to worry about that. Let's put it down here. Okay, so let's import all of those data sheets. So first one is going to be steel 1018. Okay, so what we're going to do to actually import this data is use a function called read matrix. So this is going to take whatever we're importing, whatever data we're going to import, and it's going to then make it a matrix in Matlab. So we're going to use read matrix. And remember, for me, I have my data stored in a folder called data. So I'm putting data / group 2 / 1018 steel dot text. Okay, and then we can run this. And then you see on the right hand side, I have a matrix now that's in my workspace. So I can open this up by double clicking on it, and we have our text file here that we just imported. So the first column, I think that was the crosshead position, which we don't care about. Second column is the load, so we do care about that. Third column is the time, don't care about that. Fourth column is the extensometer, or our deformation. We care about that. Okay, there's a question for, I forgot what the semicolon means. So that suppresses everything. So if I didn't have that semicolon and I run this, I get that entire output now in my command window, which, you know, we typically don't want.
I have a question.
Mm-hmm.
The read matrix is just pointing to the data in the folder, right?
Yeah.
Okay, thank you.
Mm-hmm. Okay, so I'm going to suppress this again because I don't want to see that output in the command window. Okay, and then we want to import our other two sheets here. Did I not copy it? Copy it. Oh, that's weird. The copy command is Alt W on here. That's weird. We can change that, but I forget where to go. Okay, so steel 1045. And we're going to make another one for aluminum. Alright, and let's change this. 1045. And then we need aluminum. And what did I call that? Okay. Aluminum 6061 T6. So I ran this again, and now I have a matrix for aluminum, matrix for 1018 steel, and another matrix for 1045 steel. And the last thing we need to import is our geometric data. So I'm going to call this geo read matrix data slash group 2 slash geo.xlsx. And if I open geo, this is all of the geometric data that we had. So I'll actually open up that spreadsheet just so you can see what it looked like. Alright, so this is the spreadsheet that we had. This is for group 2, so your spreadsheet might look a bit different. But for group 2, this is how it looks. So for us, all we care about is this column here. This is column 1, 2, 3, 4, 5. Okay, column 5, this is our original average diameter. And then we care about, I think it's column 9. Yeah, column 9. This is the average final diameter, that fracture diameter. Alright, close out of that. Okay, so we have everything that's imported now. Next thing, we're going to define a few knowns. Let's go back to our script. Make a comment. So the percent sign, if you guys forget, hopefully you don't, but the percent sign is a comment. So whatever is after a percent sign, that's not actually kind of, I don't know, recognized by Matlab. Matlab just ignores it. So define knowns. First thing is our gauge length. So I'll call this init length for initial length. That's 2 inches, remember. And I'll make a comment after so we know that's in inches. And the next thing is going to be the published values for the elastic modulus. So I'll just give these to you, but in your memo, you're actually going to have to cite your sources, remember. So what I'm doing here is making a vector. This is going to hold the elastic modulus for all of our materials. So for the first one, this is going to be for 1018 steel. So this is going to be 297 and 1, 2, 3, 4, 5 zeros. Okay, next one is, and this is in units of PSI, so pounds per square inch. Next one is going to be for 1018 or 1045 steel. It's going to be 290. This is going to be 6 zeros. 1, 2, 3, 4, 5, 6. And the last one is going to be for aluminum 6061 T6. This is 99. And then we have 5 zeros. 1, 2, 3, 4, 5. Let me double check. 1, 2, 3, 4, 5. Yeah. So basically, what all I did was I went to Google 1018 steel elastic modulus. Here you go. You see it's 29,700 KSI. I just converted that to PSI in Matlab. And so here it's from AZOM. So you can click on that and make sure you get this link and you cite your sources in your memo. So again, I made this variable. I called it pub em for published elastic modulus, and this made a vector. Let's also add on another comment. So this is 1018 steel, 1045 steel, and then 6061 T6 aluminum. So if we open this up again, it's right here. Okay, this is a vector. So we have 1018 steel, 1045 steel, and then our aluminum. And we made it a vector for a good reason, because we're going to be using a for loop real soon here. And having all of these in just one vector, it's going to make things a lot easier for us later on. So we don't need to type out or basically do the same thing 3 times. We can use a for loop to do a calculation just 1 time. Okay, everyone good so far? If you haven't used Matlab in a while, maybe this is already overwhelming. I hope not, but if it is, you can for sure watch this video again once it's posted. I'm going to make a whole new section here called calculations. And the first thing we're going to do is calculate our cross-sectional area. Calculate cross-sectional areas. Actually, before we do that, I didn't see this. So first thing that we have to do is we are going to, and this is again for convenience, we're going to get all of the data that we have, all of our load and deformation data, and we're going to put it into something called a cell array. Organize, let's say, load and deformation data to a cell array. And I'll explain why we're doing this in a second. Okay. So first thing, we're going to say D, and then curly brackets 1, 1. So D, that's going to be the variable that I'm using for our cell array. You can call it whatever you want. You can call it, I don't know, data array, whatever you want. I'm just going to call it D because that's simple to type. Okay, curly brackets, they signify a cell array. And what I'm going to do is make this very first entry. This is going to be in row 1, column 1. And this will be our data for our 1018 steel. So I'm going to say S underscore 1018. That's what we imported up here on line 7. And all I care about is the data for the load and the deformation. So I want to get all of the rows, so that's what this colon means. Okay, we'll put comma, and now we need to specify the columns that we want. For us, that's 2 and 4. Let's go back here. So if I open up our text document, okay, this is the text document. So remember, the first column is the crosshead. So you see that here. Second column is the load. Third column is the time. Fourth column is the extensometer. So all we care about is the second column, that's the load, and the fourth column, the extensometer. Oh, jeez. Alright, so let me go over this one more time. So D, that's what I'm creating right now. That's going to be... What? Was there a question?
I unmuted by mistake, my bad.
Okay. So D, that's the cell array that we're creating. And the curly brackets, they signify a cell array. And again, I'll explain why we're doing accelerate in a second. And 1, 1, that means it's going to be row 1, column 1 for this entry that we're creating here. I want to do this for 1018 steel. So we have s underscore 1018. That's what we imported up here. And I want to get all of the rows. So that's why we have a colon here. And then I want to get columns 2 and 4. Okay, so always in Matlab you do rows, comma, columns. So all of the rows, again, in columns 2, 4. And if we look at this cell array now, I know it's pretty small, so the text here. But this is the cell array that we just created, so I can double click on this now, and I can open up that cell. And what we have here in column 1 is the load data, and in column 2 is the deformation data. Alright, let's go back here, and we're going to do the same thing for 1045 steel, and then for our aluminum. Okay, so now we're going to do D1, 2 and D1, 3. Change this to 1045, and we're going to change this to aluminum. Let's run it, and let's look at this again. So you see now we have 3 entries. So in our first entry, that was 1018 steel. Second entry is 1045 steel. In our third entry, that's our aluminum. So if you look at all of these, they're basically, individual matrices that we have. So we have one matrix here, another matrix here, and another matrix here. All of these matrices, they're different lengths because, for our first test, 1018 steel, that has 945 rows. Basically just because the test ran for different times, right? And then our second one has 701 rows, and our third one has 1,138 rows. So in Matlab, if you have a matrix, it has to have all of the columns need the same amount of rows. So if I wanted all of this data, all of the data for the first run, the second run, and the third run in one matrix, they would all need the same amount of rows, which they don't have because, again, they ran, for different amount of time. We could pad them if you guys are familiar with that. So I could have everything be the same length, and by padding it with something like not a number. But that's getting more advanced, so I don't want to go over that today because this isn't, a Matlab class. So we're using a cell array because I can have all of these different matrices contained within the cell array, and it doesn't matter if they're different lengths. Okay, so again, by having a cell array, I can have all of these matrices of different lengths in here, and that's okay. Alright, we'll close out of that. Okay, so now we can actually use our calculations now. So we want to calculate the cross-sectional area. And what I'm going to do, I'm just going to add this on in the first row of our cell array. You could just make a whole new vector for this or matrix, and that would be fine too, but this is just what I did last night, so I'm going to keep doing that. So we're going to make this our 4th entry in our cell array. So of course right now we just have 3 entries. I'm going to make it our 4th entry over here. So I'm going to call that D, and then 1, 4 for the 4th entry. And of course, to calculate area, we're going to do pi divided by 4 times the diameter squared. We need to put a little dot before our multiplication sign here because we're doing an element by element operation, meaning we're not doing matrix multiplication. So I'm taking pi divided by 4, and I want to multiply that by the diameter squared for steel, and I want to do that for 1045 steel and for our aluminum. Okay, so it's hard to know where everyone is at with our MATLAB skills, but if you need a refresher on element by element operations, go back to, if you took me, go back to our notes, or if you took someone else, you should have talked about element by element operations probably pretty early on in your class, so you can review that if you forget. Okay, so now we're going to multiply this by our diameter, okay? Remember, we imported the diameter up here. So we're going to do this for the average initial diameter and the average final diameter. So for my spreadsheet, those were columns 5 and 9. Okay, and then we need to square it, and again, we're doing an element by element operation. So let's go back to our geometric data sheet. Let me just open it up. Okay, so this spreadsheet here, this is for group 2. So if you're looking at a different spreadsheet, the columns for the original diameter, average original diameter, and average final diameter, they might be in different columns. So just make sure that you get those columns correct. But for group 2, original average diameter, that's in column 5. And then the original final diameter is column 9. Yeah, you could definitely post those lecture notes from Sanders too. Yeah, that's a good idea. It's probably going to help people. Okay, so there we go. Let's run this now. And if I open up our cell array again, now in our fourth entry, we have the original cross-sectional area now for 1018 steel right here, 1045 steel and aluminum. And in column 2, it's the final cross-sectional area for, again, 1018 steel, 1045 steel, and then aluminum. Alright, and we could do all of that just on one line, and we don't have to type out 6 lines to do this. Alright, next thing is going to be our for loop now. So now we're actually going to be doing, the bulk of our calculations here. So calculating stress, calculating strain, and the elastic modulus. So we're going to be using a for loop. So I'm going to say for I equals 1 to 3. And again, just like this line here, we're using a for loop, so we don't need to do 3 lines of code to do calculations for all of our 3 materials. So we have for I equals 1 to 3 because we have 3 materials. And the first thing we need to do is delete the rows that have negative load values. So if I open up our cell array, and let's look at our first one. So this is for 1018 steel. If I go to the very bottom, we have the last 2 rows, they have a negative load. And we don't want to include that because really this fractured on row 946. Okay, we shouldn't have a negative load. So we want to delete those, in this case, the last 2 rows here. Okay, and then same thing for our second material, which is 1045 steel. There's another negative load. This time it's only 1 row, but we want to delete that row. And then for aluminum, again, we have the last row has a negative value. So you could, delete all of these manually, but that's inefficient. Especially, consider if we had like 25 materials, you would not want to do that manually. So we're going to do this with our script here. So to kind of break this down, the first thing that we need to do is find where we have a value that has a negative load. And that's only going to be at the very end of the data sheet. So I'll call this neg for negative, and we're going to say d 1 comma I. So this is going to be looking at our cell array. So we're looking at this very first row, and I want to do it for all of our 3 materials. So for 1, 2, and 3. So that's why we have comma I, that's the column. So we're in the first row, column 1, 2, 3. So we're looking at that. And now I want to look within each of those individual matrices. I want to look at all of the rows in the first column because that's going to be for our load. So we're going in, let's say we're in our first pass. So we're in row 1, and then I is going to be equal to 1. So I'm looking at D 1 comma 1 right here. And in parentheses here, we're looking at all of the rows in the first column for that first entry. That's what's highlighted here. Okay, going all the way to the bottom. And then we're going to say less than 0. Okay, so if I type in neg, actually let's open this up instead. What we have here is a logical result. So this is a logical vector in this case. So a 0 means that we have a positive value in this case, and we're going to go all the way down to the very end, and you'll see that our last row here is a 1. This is actually for our third material, because we actually did a loop here 3 times. So we did it for 1018 steel, we did it for 1045 steel, and we did it for aluminum. So for our very last loop, that was for aluminum, and we have a negative value for that very last load value. So if I open this up for 3, let's go all the way down, and the very last row, you see that we have that negative value, so that's why we have a 1. That means it's true. We had a value that was less than 0. So really, this is just telling us, where we have that negative value. Okay, what I could do here real quick, just to show you guys, I'm going to show you each pass. So let's do it for the first pass. So now we're on the very first pass, and this is for 1018 steel. So you see, for the last 2 values, we have a 1. So remember, we saw that. Let's go to 1018 steel. The very last 2 values, we had negative load, which you see here. Let's go to the second pass now. So I'm going to press step again. Here we have a 1 at the very end. That was for 1045 steel. At the very end, there's only 1 value that's negative. We see that right there. And then we'll do our third pass. And again, we have a 1 at the very end. And that's for our aluminum. There's 1 negative value at the very end. See there. Okay. And then if I continue to press step, then we're out of the loop now. Because I know this is a lot of review, especially if you haven't taken Matlab in a while. But trust me, if this is like overwhelming right now, just watch this video after. Or if you have questions, you can ask me or your classmates in Discord, and we'll help you out. Get out of here. Alright. So now that we found those rows where it's a negative value, now we want to actually delete them. So maybe I should call this find rows. Okay, now we found them, so now we are going to delete them. Delete rows with negative load value. We'll say in parentheses positive logical result, which remember that was a number 1. 1 means true. Alright, so to do this, we're going to say d1 comma I. I'll explain all of this in a second. So d1 comma I, and curly brackets, and then neg, comma colon equals empty brackets. So what this is doing is we're going to look at each of our entries in the cell array, which I keep closing. I don't need to close it. So each entry in our cell array from 1 to 3. And then we're going to be using array addressing here, where we're going to be using that logical result that we just found here. And every time that there is a 1 for the logical result, we are going to basically delete that row. So, for our first material, that was the last 2 rows. Second material, the last row. Third material, the last row. So let's open this up. Okay, so currently there's 2 negative values, so we have 948 rows. Let's go back here and let's run our script. Now if we look at that again, you'll see that we deleted those last 2 rows. Okay, so there we go. So now we've deleted them. And if you want to do all of this on one line instead, you can. But then it gets, it looks kind of intimidating, especially if you haven't used Matlab in a while. So I can comment these out here. So if you wanted to do, what we did up here, just on one line, you can. So to do that, we're going to do D, 1 comma I. And then we're doing array addressing, which is essentially going to be all of this right here. Okay, I'll just type it out though. So D, 1 comma I, and then all of the rows. We're looking at the first column, that's load. We're going to check if it's less than 0. And then equals. Alright, and there we go. That's going to be the exact same thing that we just did. So I just ran the script again, and you can see that we have those last 2 rows for our first material. They are deleted because they had negative load values. Okay, so we did that. Now we can do our stress and strain calculation. So I know, some of you might be thinking that's a lot of work just to delete some rows, and in this case, yeah, maybe it is. Maybe you could have done this faster manually. But that's missing the point, Sometimes we have a lot of data. If we had, again, 25 materials here, and we had to delete rows with negative load values for whatever reason, it would be much faster to actually type out, a script instead of deleting all of those manually. Okay, so let's calculate our stress now. Stress, easy formula, right? Just our load divided by our cross-sectional area. So what I'm going to do now is make this our second row for our cell array. So right now we have 1 row with 4 columns. Now I'm going to make a second row, and we're going to have 3 columns for the 3 materials that we have. Okay, so that's why I'm calling this D, 2 comma I. So this is going to be in row 2, and we're going to have I amount of columns. And we're going to get our load here. So that's D, 1 comma I. And then we want to get all of the rows in the first column. So this right here, D, 1 comma I, that's going to look at all of our 3 materials. But once we look at one of those materials, we want to only look at all the values for the load. Let's actually pull this out. We'll do it like this. So if I'm on my first pass here, and I want to look at all of the load values for the first material. So the first thing here that I've highlighted, that means I want to look at this first value. So I want to look at row 1, and then I is going to be equal to 1 on our first pass. That means row 1, column 1, right here. So now we're looking inside of this matrix, and then this part here, that's array addressing inside of this matrix. I want to look at all of the rows in our first column. And remember, that's for the load. Okay, so everything that's highlighted here, this represents all of the load values for 1018 steel, if we're on the first pass. So we have our load, and now we're going to divide it by our cross-sectional area. I can move you over like that. Again, we have to do element by element division in this case. So now we want to do it for our cross-sectional area. Remember, we already calculated that up here. That's our 4th entry in the first row. Okay, so this is here. I've just opened up this right here, and you can see it says D 1,4. This is the cross-sectional areas that we've calculated for the original and then for the final. So if I'm doing I, 1, this is going to be for all of the rows in the first column. This is all of the cross-sectional areas for the in the original cross-sectional areas. So now if I run our script, now you see we have a whole nother row here. And if I open that up, all of these are the calculations for stress for, in this case, 1018 steel. If I do it right here, this is for 1045 steel, and then for aluminum. Okay, there we go. Now we can do this similarly for strain. Let's paste that in. And we're going to make this our third row instead. And we don't want to look at the load value. Now we want to look at the deformation value. And then we want to divide this by our initial length. So remember, we already made a variable for that up top here called init length. That's 2 inches. Remember, that was the initial length for our extensometer that started at 2 inches. And so remember, you know, I put a comma 2 here because we have, when we made our first row up top here, this contained the load and deformation data. So column 1, that was for the load, and column 2, that was the deformation. Alright, so there's strain. I guess we can write the units as well. So this was PSI for stress, and for strain, that was inch per inch. Okay, so we're making progress. We have our stress calculations, our strain calculations. Now let's calculate the elastic modulus. So remember, for that, we're going to get 2 values for our stress and 2 values for our strain. And then we're going to solve it that way. So we're going to do sigma 2 minus sigma 1, that's in the numerator, divided by epsilon 2 minus epsilon 1 in the denominator. Essentially, we're just doing rise over run to calculate the elastic modulus. Okay, so for this, it's somewhat arbitrary for what I did. So you can choose different numbers, but remember from our first lecture, let me pull this up again. 306A lectures. Okay, so remember in our first lecture, we talked about when we are going to calculate the elastic modulus that we want to get a value that's kind of up top here. That's before our proportional limit, because remember, to calculate the elastic modulus, we need to be in the elastic range. So we want to go before, actually we can go up to our elastic limit, right? Anything after that is permanent deformation. And so I told you guys, though, that you should choose a point that's kind of far up here in your elastic range, and a point that's kind of down here in the elastic range as well. So you want like a decent spread so you can avoid the effect of noise. So when we first start out our test, it's a bit jaggedy in the very beginning just because we're starting to apply that tension. So you don't want to choose a value that's right next to the origin, because you know, we're getting rid of any slack that we may have in the experiment, and then we're starting to finally apply that constant tension. So what you want to do is choose a value that's, you know, I don't know, let's say somewhere around here for your low end, and then for your high end, somewhere around here. I know it's kind of arbitrary in a sense, but you want to make sure that you're within that elastic range and that you have a decent spread. Now for us, I chose values of 200, so that's our upper value. So that's, you know, row 200. So in this case, you know, we're at row 200 here. Okay, and that would be a load of 3,520 pounds. So that's for 1018 steel. I kind kind of did this somewhat arbitrarily. You just want to be within the elastic range. So you can use different numbers than I've chosen here. I just chose 200 and I just kind of went with it. And in the end, all of the results are good. So you can just follow along with what I have, or you can choose a different number if you want. But I'm going to do 200. So we're going to make this our fourth row. So we're going to do 4, comma, I. Okay. And then we're going to do, we want to get our 2 stress values. So sigma 2 minus sigma 1. So let's do D. This is going to be 2, comma, I. So this is, remember we calculated stress here. That was row 2. So 2, comma, I. And then I'm saying get the 200th value. So this is sigma 2. Right here, this is sigma 2. Then we're going to do minus sigma 1. And here, this is the 10th value. So that would be the 10th value right here when we have 262 pounds. Okay, that's our numerator. So remember the numerator was sigma 2 minus sigma 1. Now we're going to do divided by epsilon 2 minus epsilon 1. So this will be D. We calculated our strain right here. So that's 3, comma, I. And we're going to do the 200th value minus the 10th value. Okay, 10. And also, all of our denominator here, that should be enclosed in parentheses. So let's do that. And there we go. And let's suppress the output as well. Okay, that is our elastic modulus formula. Trying to space this out so you can see it all. Okay, so you don't need to space out your parentheses like this. I personally do it just so I can better tell how everything is formatted. So, I don't want to be a broken record, but if you haven't used Matlab in a while and you look at this and you're saying, what the hell is going on? You're going to want to really break this down afterwards and play back this video and make sure that you go step by step so you can understand it. If you haven't used Matlab in a while, you're probably thinking, this is ridiculous. Why would I not just use Excel? Trust me, this is going to be way better for some experiments. Maybe not for this lab, but once you get to like 306B and other labs that you got to take, using Matlab will be way faster. And for other classes too, you're going to have to use Matlab. And if you have knowledge in how to use it, you're going to be in a much better place than some of the other classmates. And it's just a good skill to have too as well. And that's our elastic modulus. Now let's do the percent error. Okay, percent error. Here we go. This is the percent error for the elastic modulus that we just calculated versus the elastic modulus that's published. Yeah, so when I actually took this class myself, this lab, I know if I was told that if I had to use Matlab, I would be shitting my pants because I didn't know Matlab well at all back when I took this class. But, I had to use Matlab later on for some of my other classes because I wasn't strong in it. It was really hard to do some of these projects that I had to do in the classes. So that's another reason why I'm doing this for you guys, to hopefully help you guys strengthen your skills in here so you're in a better spot later on. Okay, so fourth row, we can see the elastic modulus that we just calculated here. Let's just output this in the command window. That's D4. So this is all of the elastic moduluses, moduli that we just calculated. So this is for 1018 steel, 1045 steel here, and then aluminum 6061 T6. Alright, let's calculate that percent error. Okay, question. why do we write I if we are going to use row 200? So I think you mean I right here. So this first part here, this is just to select the row and the column that we have in the cell array. So let's say that we're in our first pass, which is for 1018 steel. That's going over here, and that's saying that we're in row 2, and then on our first pass, I is going to be equal to 1, so that's this value right here. Then we go on the second pass, that's going to be this value here. Third pass, this value here. So the value for 200 is actually going inside of each of these matrices. So again, if we're on the very first pass, we're in D 2, 1, that's this matrix here. And now we're going to go inside of that matrix, and then we're going to get the 200th value in that matrix. All right, does that make sense? It's kind of like layered array addressing. This is array addressing for the matrix we want to look at, and then inside of that matrix, this is the row. Okay. All right, so next thing is the percent error. So I'm going to make this now the 5th row in our cell array. So I'll call this D 5, I. Okay, so percent error, we want to get the absolute value because there's no negative percent error. That doesn't make sense. So we're going to use the absolute value. And we're getting in the numerator our calculated elastic modulus. Subtract that from the published value, and then divide all of that by the published value. Multiply it by 100 so you get a percentage. So absolute value, D 4, I, so this is the elastic modulus that we just calculated. We're going to subtract that from the published elastic modulus that we made earlier. Okay, that's our numerator. Then we're going to divide this by the published value again. Pub in I. Close out our parentheses for the absolute value. Multiply this by 100. So remember earlier on we made a vector for the published elastic modulus, and we had it organized as a row vector. So our first value is for 1018 steel, second for 1045 steel, and third for aluminum 6061 T6. And now if we run this and we go back to our cell array, you can see our percent error. So for 1018 steel, that percent error was 3.48%. For 1045 steel, 0.95%. And for aluminum 6061 T6, 0.28%. So really good numbers actually. Usually I think it's actually a little bit higher from past semesters, so maybe we just had better samples this time around, or maybe you guys just did a better job in the lab, but those are pretty damn good numbers for the percent error. Alright, so I know this is kind of carrying on now, but we're almost done. Next thing is the yield strength. So if we made a plot for what we have now, you would see our stress strain curves. I think all of them are really gradual, so it's hard to find a defined yield point. So what we're going to do is find the yield strength. And remember, we find the yield strength by using our offset method. Let's open this up. So remember, the yield strength is when we use our offset method. So if we're looking at this blue curve, this is our stress strain curve. There's no well-defined yield point. So we need to find the yield strength by using our offset method, where we go to 0.02% of strain, or sorry, 0.2% of strain, which is 0.002 inches per inch. And then we draw a line parallel to the line that we have in our elastic range. And then we find this intersection point for when this line intersects with the stress strain curve. And this corresponding y value in this case, that's going to be our yield strength. Okay, so that's what we need to calculate now. So the first thing that we're going to define is that line, that I should have kept that open. So first thing we're going to do is define this kind of dashed red line here. We're going to make that line. So I'm going to call this offset x for our offset method. This is going to be our x data. So our x data is going to start at 0.002 inch per inch. We're going to use a very small step size. I guess it's not really that small at this scale, but we're using a step size of 0.001. And we're going to a final value of 0.006 inch per inch for our strain. So we are starting at 0.002 and we're going to a value of 0.006. This is for our data, so I could choose, a different final value. I could do like 0.01 inch per inch if I want, and our line would just go further. That's it. So that's our x data. So in Matlab, you always need to supply your x data and your y data for a curve. So we'll define our y data. We'll call this offset y. Okay, this is going to be the 4, 1. This is our elastic modulus data that we calculated here. So I'm doing this right now for 1018 steel because I have 4, 1. And then we have times offset x minus 0.002. So what is this? This is y equals mx plus b. That's all it is. So our slope is m. Our slope in this case is the elastic modulus that we calculated here. And then we have y equals m times x plus b. So our x data, that's going to be our offset x data, and I'm doing minus 0.002 for that offset. And then b, we don't have a y-intercept that's offsetted, so it's just at the origin. Again, you might want to look back at this again to kind of refresh yourself to understand what's going on. But you'll see, we're actually going to use this data later on, and we'll plot this as well. And you can see that that line that we essentially are creating here is correct. So I guess for now, just kind of roll with this, but we're going to plot this in a bit, and you'll see that it's that dashed red line that I just showed you from the lecture. So now we want to find that intersection point, and this is when you need that mapping toolbox. So to use this function here to find the intersection point, you need that toolbox. So in brackets, and you have to do this with square brackets here, we're going to call this int x and int y for intersection point, the x intersection point and the y intersection point. So we're going to find these, we're going to solve for them basically. And what we are going to care about in the end is this y intersection point. That's going to be the yield strength that we have. Set this equal to poly x, poly y. That's the function we got to use. And the syntax for this, good thing I pulled up. We have x1, y1, x2, y2. So we have basically our first curve and then our second curve. Pretty simple. So we're going to do d 3, 1. This is the strain data for 1018 steel, and comma d. Now we need to give the stress data. So we're going to do d 2, 1. That's our stress data for 1018 steel. Then we're going to do offset x and then offset y, which is what we just defined. So that's our x data, and then we have our y data specifically for 1018 steel. I can run that, and then we get our value for the intersection point. I don't really remember this giving 3 values in semesters past, but it's just probably because of plus minus, like a little bit of tolerance. All of these are just about the same value, so you'll see in a second once we plot it to you that it is the case. So we have the intersection point basically. We just solved for the yield strength. So you can get that from, again, from this int y vector that we just made. Alright, last thing is plotting. I know this has been kind of a long lecture, so if you're still in here, cool. I'm glad you stayed. Let's see how many people are even in here still. There's actually still a good amount of you. Okay, so we're gonna do figure, visible, and then on. You don't have to do this, but I would recommend it once we start making multiple plots. And maybe you don't want all of the figures showing up every time. You can change, the ones that you don't want to show up to figure, visible, and then off. Okay. So now let's make our plot. So we're gonna make our stress strain plot right now. So, some of you might be thinking that we could also write all of these plots in a more efficient way too, like with a loop. We could do that, but that's just gonna make things even more complicated. So we're gonna do it just, each plot individually. So right now we're gonna do it for 1018 steel. So let's do plot D3, 1. So we need to give our x data first. Okay, we need plot x, y. So 3, 1, that is our strain data for 1018 steel. And now we need to give our y data, which will be 2, 1. That's going to be our stress data for 1018 steel. And we're going to make this a blue line, so that's why we have comma, and then within the apostrophe B for blue. And you don't have to do this, but I'm going to make the line width a bit thicker than the default. So I'm going to make it a line width of 2. And let's just run that right now. There we go. Don't worry about this warning. This is just for my computer for graphics. Alright, here is our stress strain curve for 1018 steel. There we go. So again, it's not it's an okay defined yield point, but it's not great. So that's why we're still going to use that yield strength instead. Now let's make this graph a bit prettier. Let's add our labels and whatnot. So x label, let's call this strain, and we can say inch per inch. And y label, it's going to be stress. That'll be psi. We can add a title. This is going to be 1018 steel. And then there's a few more things I want to change. So if we run this, you see that we have exponents along our y-axis. I'm going to get rid of those, and I want you to get rid of them as well because it's harder to read when it's like this. Just at a glance, So we're going to get rid of those exponents. To do that, we need to type in AX equals GCA. Basically, this stands for get current axis, and this gets all of the properties for this plot that we just made. And now we can type in AX.y-axis. The capitalization does matter here, so make sure Y and A are capitalized. Dot exponent equals 0. We'll run that. And then we got our new graph here. And the exponent is gone. Actually, sometimes capitalization doesn't matter. In this case, it does. Okay. Alright, so there we go. Now it's a bit prettier. And yeah, we could also change the formatting here to use LaTeX formatting. I didn't do that this time around, but we can basically just make these labels a bit prettier, or we can actually have like a fraction. So we can really have a fraction where it's our numerator is actually on top and the denominator is on bottom, not displayed kind of side by side like this. But that's okay. That's kind of superfluous stuff, if I use that word correctly. So we don't need to worry about that. One thing that you guys have to do in the deliverables, which I didn't talk about, but I uploaded the deliverables online, so we can go to files, or you can go to assignments. So I'll show both methods. So we can go to files, experiment 1, and then, okay, oh yeah, right here, stress strain deliverables. Okay, we can click on that, or you can go to assignments, memo 1, and the deliverables, I put them right here too. We'll click on that. This will open up. So this is going to show you everything that you have to do for the memo. Okay. So compute stress and strain, we just did that as a class. Plot stress and strain, we just did that. So there's going to be 2 things you need to do. So one of them is going to be for the entire range, which we just did. And another one is going to be for just the elastic range. So you're going to kind of compress this down. You can go like maybe up to the yield point. Basically, I just want a more zoomed in picture that's going to show the elastic range. Okay, then you need to label parts on your curve. So I'll show you how to do that right now. And then error analysis, that's going to be the elastic modulus that you calculated compared to the published value. So we need to compare values that we calculated to the published value for elastic modulus, which we just did. The yield strength, which we calculated, you just need to solve the percent error. So you can find the yield strength online as well. And then the ultimate tensile strength, got to compare that too. And then the percent reduction in cross-sectional area. So we aren't going to do this as a class, but that's a simple calculation. You can do that. And then your expected sample calculations, I show you that as well. So make sure you include a sample calculation for all of these. And remember, this is due on the 30th of September. All right, let's go back here. So to do a label, you can type in G text, and then whatever your label is going to be. So let's call this yield strength. Okay, and we can run this now. Oh, dang. Okay, let's run it. And you see that I have these crosshairs here, and that's going to let us choose wherever we want to put a label. So let's say the yield strength is around here. We actually got to show this in a second, but we can just click down and there's the yield strength. You can also change a lot of stuff, so you can add in whatever the color you want it to be. So I can make this like red. Okay, so I'm showing you that because maybe you want to have different labels, a different color, up to you. How to find the ultimate tensile strength. So to do that, now you can do this actually in your script, but let's just do max of D 2, 1. And what this is doing is getting our maximum value for stress for 1018 steel. And there we go. That's our ultimate tensile strength. Let's see. Okay, so yeah, now we're going to plot that offset curve that we just showed, and that'll be the last thing. Oh, how sad. We lost some people now since I talked about how many of you are still here. Okay, so we're going to type in hold on. So we need to, if we want multiple curves on one plot, we need to use the command called hold on. Okay, this will allow us to have multiple curves. And now we're going to plot offset x, which we defined up here. This is our x data. And then offset y. So this is our y data specifically for 1018 steel. And let's make this a blue dotted line. Okay. And then we're going to say hold off because we're done with the curves that we want to put in here. Let's run it again. It's kind of faint. Hopefully you guys can see it, but we have our blue dashed line. So this is our offset curve. So it's parallel to our elastic range line right here. And this intersection point, that's the yield strength. I didn't mean for this to be down there. Let's do one more thing. Let's type in, let's go over here, y line. This will give us a horizontal line corresponding to some y value. In this case, we're going to put this for our intersection point, our y intersection point, which is what we calculated here. Remember, that's the yield strength. Let's add a little comment. Int y equals yield strength. So if I do y line int y, and I'll make this like a black dashed line. Okay, let's run this now. Let me do it again. Oh, dang it, I just closed that in Matlab, sorry. Okay, let's run this again. There we go. Looks bad now that I'm changing it a bit. Okay. So this is to show you kind of like the proof that we did everything correctly. So remember, this dashed line is what we made. We defined the x data. We defined the y data that was offset x and offset y down here. Specifically for 1018 steel, at least regarding offset y. And then our black dash line, this is just a horizontal line that corresponds to the y intersection point, which is our yield strength. So we see that, yeah, that corresponds to this intersection point that we have for the offset line that we made to our stress strain curve. So that's our yield strength right there. So we know that we calculated that part correctly. You don't need to show these, this dotted line and this dash line in your memo. This is more just to, again, show you guys that yes, we calculated that yield strength correctly. Okay, there we go. So that's it for the data reduction, for this video as a class. And I know it's a lot of stuff, right? But yeah, so that's it for today. That's all I had planned. So we did the lecture, we did our data reduction. I'm going to record this, or I'm going to upload this video as soon as I can. It takes a while to process on YouTube till it's like actually, good quality. But if you want to watch this back, definitely do that. I would definitely recommend that you do that if you're kind of not up to date with your Matlab skills. So yeah, definitely take a look at it. And if you have questions, you can, first try to ask just in the general chat in Discord, and hopefully a classmate knows the answer to your question. But if there is a lot of confusion, feel free to, to at me in Discord, and I'll respond there as well. If you have a question though, post it again in the general chat, because if you have a question, most likely other people do too, and I want to answer it so everyone knows the answer to that question. Okay, so that's it for today. So you guys are free to go. Remember, your memo is due on September 30th. And next week, we're going to have our second experiment. So we're going to be meeting in person next week. Alright, so thanks, guys. Have a good weekend. If you have any questions too right now, I can answer them too.
Professor,
Mm-hmm.
I wanted to ask about figuring out how to, make it. So I have the script written down. I just want to know, how do I figure out how to get my stress, strain, and elastic modulus?
Yeah, so that's just all of this right here.
Okay. Is there anything that, like, for the command window, what do we input to get that answer though?
You don't need to put it in the command window. You can if you want, but I would just go over to the right-hand side to the workspace, and I would open up that cell array that we made. And then, so stress, that's the second row, so that's everything in here. Third row is strain, and then fourth row, that's the elastic modulus, so that's like the most important calculation that we did today. So you could just kind of look at it that way.
I guess I'll just have to yeah, Hmm.
Is it not showing up for you?
I'm gonna share my screen and then I don't know. It's
Okay.
disabled. Never mind.
Yeah, no, I'll enable that right now.
Okay.
Okay. Should be able to share now.
Yeah. Do you see it now?
Yeah.
So I'm here. Would it be this one?
Yeah. Uh-huh. Yeah,
It shows
so
like this though. I
yeah,
don't know.
it's the same that I had. So row 2, all of that is your stress. Row 3 is the strain. Row 4 is your elastic modulus, and then
Oh, so like all this would be
yeah, all of that is your stress data
mhm.
throughout the experiment. Yeah.
So then, so which one? Alright, so sorry, I'm just very confused right now. My bad.
Very good. So I've commented to you in the script, but row 2, all of that is your stress data. So row 2, column 1, that's for 1018 steel. Row 2, column 2, that's for 1045 steel. Then row 2, column 3, that's for the aluminum.
Mm-hmm.
And then row 3, same thing, but all of that is for strain.
Mm-hmm.
Row 4, that's the elastic modulus that we calculated.
For each one.
Yeah.
Oh, okay. And then
And
row
then
5 is our
row 5 is the percent error.
percent error.
Yeah.
Okay.
So
what
it
about
looks
this
like
one over
the
here?
column 4, in the first row, that's the cross-sectional area that we calculated, and then the others are just empty. You don't need to worry about those.
Alright then. So we just have to write these down then?
Yeah.
Okay. Alright then, that makes sense. That makes more sense.
Okay.
Yeah, I haven't done Matlab in 3 semesters, I think. So.
Okay. Yeah, I know that's probably a lot at once.
Yeah. Alright. Are we gonna turn in our scripts, or do we just have that just in our back pocket?
You can just keep it in your back pocket, like you said.
Alright then, Professor. Thank you very much.
All right. Anyone else?
All right, take care.
All right. Thanks. You too.